to Software Engineering 2FA3 Discrete Mathematics with Applications 2. Today we're going to be starting a new topic, the topic of push-down automata and context-free languages. So here's an outline for this topic. We're going to have some introductory material. Then we're going to talk about context-free grammars, various kinds of other grammars. Then we'll move to push-down automata, and then we'll show the equivalence of context-free grammars and non-deterministic push-down automata, and we'll end with some discussion about applications and a summary. So before getting to the really technical material, I would like to make some introductory observations. The first is that we've been talking about regular languages. We mentioned that regular languages can be specified by DFAs, NFAs with epsilon transitions, and regular expressions. We'll see later that they can also be specified by regular grammars, which we'll define what that means down the road. Now, regular languages are very special sets of strings. We need to keep this in mind. Only a few special sets of strings are regular. So most sets of strings are not regular. Here are some examples. The set of strings AN, BN, where n is greater than or equal to 0. The set of palindromes over a finite alphabet. A palindrome is a word that reads the same from left to right, like just a second, like racer. Racer reads the same from left to right as a palindrome. And then another kind of a set that's not regular are sets of parentheses that are balanced. So they're sets that look like this. That would be a member of this set. This would not be a member of that set. And we can see that a to the n, b to the n could not possibly be regular, because if we had a NFA like this, so let's say here we accept a bunch of A's, and we have something like this. Let's say these are both. Well, this NFA would accept the language M, it would accept this language. But M and M are both greater than or equal to 0, but they're not necessarily the same. And so if we started with this NFA, we wanted to change it into an NFA that accepts this, we can start accepting A's, and at some point we have to start accepting B's, and we need to accept the same number of B's as the number of A's. So we would need somehow to remember how many A's we accepted. And how many A's we could accept. It could be any number. It could be a very large number or a small number. Basically, it's an unbounded number. And so in order to remember how many A's we accepted, we basically need an infinite amount, or potentially infinite amount of memory. While in an NFA, we have a finite amount of memory. So that's an informal argument to show that this cannot possibly be a regular language. So we're going to look now at a bigger class of languages, context-free languages. These are specified by two ways: context-free grammars and non-deterministic push-down automata. So they're specified by a grammar and by a kind of automaton. And the three examples here are all context-free languages. And it's interesting that almost all programming languages are context-free languages. That's maybe the main motivating reason why we're so interested in context-free languages, because programming languages are context-free. But again, context-free languages, like regular languages, are very special. The vast majority of sets of strings are not context-free. And here's an example of a non-context-free language. It's A to the n, B to the n, C to the n, where n is greater than or equal to 0. Okay, to get warmed up a bit, and rather than jump right into some of the definitions we're going to see later, let's think about the English language, and let's suppose we are going to develop a grammar for English, and this will be a context-free grammar. So what we could do is we could start off with the following rules, that whenever we have a sentence can be, whenever you think of a sentence, we can think of a sentence as a noun phrase followed by a verb phrase. And notice this is a space here, and this is a period. And so we can build sentences by thinking of sentences as noun phrases and a verb phrase where they are separated by a space and they end with a period. And then noun phrases we can think of as an adjective followed by a noun phrase, or a noun phrase can be thought of as just a noun. And we can think of a noun as one particular noun, cat, and we can think of an adjective as one particular adjective, black. And a verb phrase we can think of as an adverb followed by a verb phrase, or as just a verb. And a particular verb will be sleeps, and a particular adjective will be quietly. So this is a simple grammar. It is actually a context-free grammar. And we can use these rules to create derivations that produce sentences of English. So I'm going to show you how this is done. So here's a sentence that I want to generate, I want to derive. So here's my derivation. I start off with the sentence in angle brackets, and then I know by one of the rules a sentence is the same as a noun phrase, space, verb phrase, period. So I can go from sentence to this whole thing. And now I can go from a noun phrase to an adjective followed by a noun phrase. And I can go from an adjective to black. And I can go from a noun phrase to just a noun. And I can go from a noun to just cat. And I can go from a verb phrase to an adverb and verb phrase. An adverb I can go just to quietly. And a verb phrase I can go to a verb, and a verb I can go to sleeps. So I get black cat quietly sleeps. Now there are some problems with this. If this is a sentence of English, the B should be capitalized. And we probably should have an article, either the black cat quietly sleeps or a black cat quietly sleeps. This would be an unusual sentence to just say black cat quietly sleeps. So that's a quick example of a context-free grammar for a little piece of English. So I have a question for you. Can a grammar of this kind be constructed for the entire English language? Yes or no? I'll give you a moment to think about this. Well, welcome back. This is actually to a certain extent an open problem. Certainly a large chunk of English can be constructed using a context-free grammar. But people are arguing whether all of English can be generated from a context-free grammar. So the answer is sort of like, it looks like it's probably no, but there's not a consensus that it really is no. Programming languages are context-free. Natural languages like English or German or Arabic and so forth, these languages, it's not so clear whether they're context-free. Okay, so now I want to look at a system called BNF. This is a system for presenting context-free languages. It's named after Backus-Naur. Backus-Naur are two very famous computer scientists, both Turing Award winners. So this is a context-free grammar for a Pascal-like programming language. Now we're giving a simple version of BNF. There are more elaborate versions of BNF that have been developed. So this is a context-free grammar for a simple programming language. So we have these things. Each of these is what's called let's go here. So this grammar consists of a finite set of production rules. The rules are recursive and alternates are separated by vertical bars. So if we go back up to here, these are the rules. We have a whole bunch of them. And some of them are recursive, like here, a statement list consists of a statement or a statement with a semicolon and a statement list. So basically a statement list is a list of one or more statements. And notice the vertical bar here gives us an alternative. And then another thing to notice is that expressions that have these angle brackets are non-terminals, and all the other symbols are terminals. When we do a derivation, we're going to end up with only terminal symbols. So non-terminals are meant to generate strings of symbols from our alphabet, which are non-terminal symbols. So you see we have all of these here. On the left, these are all our non-terminals. And when we do a derivation, that's just going to be a sequence where we have our starting non-terminal, and then we keep replacing non-terminals with what's on the right-hand side according to their rules until we end up with a string with no non-terminals. So here's an example of a derivation. So this is a derivation of the assignment of 5 to x. So we start with the statement. Now one kind of statement, if we go up to our statement, there's several kinds of statement. One kind is it's an assignment statement. So we're going to choose that one. And then assignment statement, what is that? Well, assignment statement consists of a var in curly brackets, colon equals arith expr in curly brackets. And so we go to here, and then the possibilities for var, one of them is x. The possibility for arith expr is constant, and one of the possibilities for constant is 5. So this is a derivation. It's a sequence of strings where these strings are composed of terminals and non-terminals, and the last string is the thing we derived, and notice there are no non-terminals here. And so the language of this grammar is a set of all strings that we can generate by this grammar in this way. Okay, so here's a final question about BNFs. A BNF defines the blank of a programming language. Okay, welcome back. Well, the answer is syntax. It defines the syntax of a language. And we can use a BNF to help define the parser of a language, where the parser of a language basically takes a string and it shows how this string is a member of our language. The BNF says nothing about the semantics of the programming language. If we go back up here and look at this BNF, it doesn't tell us anything at all. We don't know what a while loop should do, but we don't know if this is really going to do it. Maybe in this programming language, while loops do something different. There's nothing here about the semantics. Okay, so this completes the first part of this new topic, and we will continue next time by looking precisely at what context-free grammars are. Today we saw a couple examples for the English language and simple programming language of context-free grammars, but we'll look at the basic definitions next time. So see you then.